Okay, it's 10:25. Let's get started. So I guess I'll go until about 11 or 11:05, and then we do the same with questions and stuff, and then we're done for today. Close this. Okay, so once we have a beam from our accelerators, whatever facility we choose to use, we have a beam. Now I'll go through a few steps of how we can measure some of these reaction cross-sections. There we go. So the idea is rather simple. If you want to measure the yield of a particular reaction, you need to know how many reactions happened divided by the number of beam particles. So in the end, you get that would be the cross-section would be that number of the yield of the reactions divided by the number of target particles. So I put it like this. So we need three things. We need the number of target particles, we need the number of beam particles, and we need the number of reactions that happened. And I'll go through briefly some of the techniques to measure all of these. Again, you might have experience with higher energy beams, different kinds of beams. So this would be, again, more in the astrophysical reactions, the energies that we are talking about, and the target thicknesses that we're talking about here, which are probably a lot more thin than what you're used to. Okay, so starting with the target particles. The classic way of measuring target particles in our field, the low energy nuclear physics community, is called Rutherford backscattering, or RBS. The idea here is that you have a beam that goes and hits your target, and if the beam interacts, and then it scatters backwards. That's why it's called Rutherford backscattering. It's from the classic experiment Rutherford did, where they were shooting alpha particles on a gold target, and then they saw the alpha particles coming back. So if your, let's say, alpha particles interact with the front surface of the target, then they would come back and have whatever energy they have, and it will be a high energy, relatively high energy. And this would show up, let's say, in our scale here, this would show up here. But if the alpha particles go through the target and, let's say, interact all the way at the backside of the target, and then they also have to travel through the target again, losing more energy, and then come back and make it to your detector, then they lose quite a bit of energy. And so then those particles would show up somewhere at a low energy. So the energy width of this distribution is highly sensitive to what is your target thickness. Now you cannot apply these to very thick targets. This will get, thicker and thicker, meaning more and more energy loss. And at some point, it's what we call an infinite thick target, infinitely thick target. So this, instead of just being a distribution like this, it goes all the way to zero, and then you cannot tell your target thickness anymore. A real experimental data looks something like this. This is a molybdenum-92 target. This is actually from my thesis, PhD thesis from 2007. But this is a classic technique, and the idea is simple. So this was a thin molybdenum target sitting on an aluminum backing. So this is the energy loss through the molybdenum target. This is the energy loss through the aluminum backing, and it goes all the way down to zero. That's the infinitely thick target that I was talking about. So you can apply this technique. The cross sections for all of these are very well known, the angles here and so on. So the only unknown in this whole scheme is the thickness of your target, and you can get the thickness of your target in a very accurate way. This cannot be applied to everything. If my backing was not aluminum, but it was something heavier, tantalum is a common backing material, then this edge here would show up at higher energies than molybdenum. The location of these peaks depends on the Z of the target. And so instead of here, this would be over here. And it would also have a much higher cross-section, so it would probably go somewhere all the way up there and down. So then the molybdenum might be just a little blip on top of the thick tantalum distribution. So it depends on what you have, and you can use different techniques. But this is a classic. And then once you have typically what we get here is you get the target thickness, and based on the mass of the atomic mass and Avogadro number and whatnot, you can get the number of target particles. This is our goal. Okay, tools to do that. Typically what we use is silicon detectors. These are silicon surface barrier detectors. They are great for measuring charged particles. If you're not familiar with this technology, these are semiconductor detectors. The idea is that you have some distribution of charges in your material here in your detector, and then have a region of the material of the silicon that is empty of charges, that's depleted. So you apply some voltage and you empty the charges from that, and the positive charges go on one side, the negative charges go on the other side, but you need a region that is depleted of charges. And then when a particle goes through and deposits energy in this volume, what that means is that it creates charges, and those charges can then be collected. And once they're collected, you have an electric signal that corresponds to the amount of energy deposited in that part of the detector. So then you can have an electric signal. The same detector you can use in a much simpler way, but the accuracy is less, where you would have, I should say the previous setup requires an accelerator to do. If you want to do just a quick and dirty kind of measurement, you could do it with just an alpha source. And those are available a lot more easily than having beam from the accelerator, where you would have your alpha source and your silicon detector here. You measure the energy of those alpha particles, and then you put your target in between. And now the alpha beam will lose some energy before making it to your detector. So you get from a signal that looks like this to a signal that looks like this, lower in energy and thicker. So it's not as accurate as the Rutherford backscattering, but if you just want to have a rough number of how thick is that target, then you can do that. And there are many other techniques. You can measure X-rays, so use an X-ray beam to excite the atoms in your target, and when they de-excite, you get X-ray measurements. Again, they're sensitive to the target thickness. There's a lot more ways that you can measure the target thickness. If the sample is radioactive, so when we're talking about radioactive targets, then you can measure the activity of the sample, and again, this way get your number of target particles. Now switching to the number of beam particles. Again, with stable beams or with any kind of beam that is a very high intensity, this is a relatively easy thing to do. You would have the beam go through, maybe you have some collimators here to align it well, and then here's your target, detectors around it. If the beam intensity is high enough, because the beam carries charge, as soon as the beam is interacting or deposited onto your target, that charge, you can collect that charge into an ammeter. And so then from the current that you're measuring in your ammeter, you can tell how much charge did your beam implant onto your target. So this is a classic technique that has been used with stable beams for many, many years. And some radioactive beams you can still do because they're high enough intensity. But typically the radioactive beams are much lower intensity. So then we need to use different kind of techniques. Yeah, this is just an example here to maybe a detail, but maybe not. So if we would have a proton beam coming here, the proton beam just has a charge 1+. And so then it would deposit for every beam particle would deposit the charge of the electron, 1.6 × 10⁻⁹ coulomb. But if you would have a heavy beam like a krypton here, which is a 27+, every beam particle doesn't deposit just a single electron. Every beam particle deposits 27 times the charge of the electron. And so you need to know very well what is the charge state of your beam if you're going to use this technique to measure. And typically we do know it, we need to be careful. Okay, if we're going to measure radioactive beam intensity, then typically we use detection techniques, any kind of detection technique that we can think of that is appropriate with our setup. And there's many, many, many options, and where we're typically measuring one particle at a time as they come down the pipe. So you could put a thin detector in the path of your beam. And then as the beam interacts with this detector, then it could just, you measure what's going on. The problem is that for astrophysics, these beam energies are typically very low. So any kind of material you put in the path of your beam, this will destroy or stop your beam completely. So this is not ideal for just measuring it all the time, but you could put it, I don't know, every 30 minutes, depending on how stable your beam is. You can put it every 30 minutes, every 10 minutes, every hour, and just do a 2-minute measurement and take it out just to check what is the intensity of your beam every once in a while. And then it assumes that for the rest of the time, your beam intensity is stable. You could have some kind of a thin target material, or not exactly target, but some kind of thin material here that will not interrupt your beam very much. It will still go through, but when the beam interacts with this material, you can have either backward angles or forward angles. You can have, again, some silicon detectors and measure what's going on with your beam. You can put this kind of same detectors right around your target if there's enough space, and do the same thing. You can have a detector after your target, assuming the beam goes through the target and makes it after. You can put some kind of a detector after the target. And you can also grab the target or whatever is after the target and later on measure the activity if it ends up in the radioactive isotope. So many options here. I'm just giving you a little flavor of the options, and depending on the experiment, we can design the most appropriate thing. The most, I will say, effort in these experiments goes to measuring the yield of your reaction. So the number of reactions that are coming out. And again, depending on the type of experiment you do, regular kinematics, inverse kinematics, there's different techniques that one can use to measure how many reactions actually happened. So I showed already the regular kinematics thing and just some examples of where in the world there's this kind of stable beam facilities, or in red, it's the neutron facilities. There's different detectors that can be used that I'm going to come back to later, but I wanted to mention that the advantages of regular kinematics is that you can use very high intensity stable beams. And these are all very well developed techniques because they've been used for 50 years or so. But the disadvantage is that we cannot use them for everything. So there are some targets that you cannot use it for, if they're radioactive, if they're the material doesn't work, they're, what's the word I'm looking for? I'm forgetting that, toxic, whatever the problem is. Okay, so as I said, there are many different ways that you can measure how many reactions happen. And I showed this level scheme earlier, where I showed that one of the ways that you can do these measurements, and probably the simplest way because you don't need a very complicated piece of equipment, is through activation. So you do your reaction in your accelerator, and if the final result of that reaction is a radioactive nucleus, then you can just shoot your beam for an hour, for 10 hours, for however long you want to shoot the beam. And then you don't measure anything, you just activate your target, you just do the reactions, and then you get that target out and you put it in a separate room, something like this here with a single detector. You put it in front of the detector and you measure the activity. It's like a radioactive source. You just measure the activity that's coming out after a while, depending on the half-life. And so this is the cleanest measurement you can have, because then you don't have to worry about beam-induced background, any kind of background. You have this isolated detector, you put a LED castle around it, and it's just, it's a clean, much cleaner measurement. The problem is that you cannot apply this to everything, because it's you have to have an appropriate half-life for the final target in order to do this measurement. If you want to go in beam, you can do it in two main ways, two different ways. One is to put multiple detectors around it. This setup has 4. I think I have some setups later. Sorry, I went too far. Yeah, I have some setups here that have multiple detectors, and you can even go to 4 pi. I thought I had a picture of a 4 pi, but it looks like I don't. Anyway, so the idea is that you can measure the gamma rays that are coming out of the reaction directly as they're coming out of the reaction. but you can't just measure at one particular angle because there's an angular distribution to those gamma rays coming out that depends on the properties of the states where the gamma rays are coming from. So you need to measure at multiple angles simultaneously and do angular distributions. So this tends to be a very time-consuming process of doing that. You have to analyze a large number of detectors, do angular distributions, multiple excitation energies, and so on. And there's also the main disadvantage is that when you're trying to measure every single individual gamma ray, you never know if you missed something. There could be some weak gamma rays, some very high energy gamma rays that your setup is not appropriate for. So that you could be missing intensity, which means that your cross-section would not be 100% correct if you're missing something. So to fix that problem,
one quick question.
Oh, yeah.
Thank you. Are there any of these fixed target style setups that are designed for intercepting and measuring cosmic rays?
For the cosmic rays, I think with the stable beam facilities, if cosmic rays are a problem, then that's when you go underground that I mentioned earlier. Another way that we have dealt with cosmic rays, I've done it in inverse kinematics, but I'm pretty sure you can also do it in regular kinematics, is to have some kind of a pulsed beam, and then you measure kind of beam on, beam off. And so then during the beam off period, that's when you check what is your background, and you can subtract that later. Or you can event by event identify, okay, this is the beam on period, I only measure that and reject everything else. So yeah, there are some techniques that you can do that. We've also built active veto detectors, so some kind of a detector that will go on top of your setup. So if a cosmic ray interacts with the top detector and with the detector you have, then you can reject that event because it was a cosmic ray event. So yeah, there's some techniques. Okay, so coming back to the gamma rays, the solution to not missing those little individual gamma rays is what is called a summing technique, where I have here just a cartoon example of, let's say we have a P gamma reaction, and when you have the reaction, you populate your final nucleus at some high-lying state. Up here, it's called the entry state. And then this nucleus will de-excite either by emitting a single gamma ray going down, or maybe it's 5 gamma rays going down, and so on. So if you have a large enough size detector, then that detector would collect all of the energy coming from all of these different gamma rays that are in a cascade. So these gamma rays here, 3 gamma rays, they're all coming within a few femtoseconds of each other. So within the time resolution of your detector, you cannot tell them apart. You just see the full energy that's coming into your detector in principle simultaneously. But you can sum it all up. And then in terms of getting a cross-section, that's all you need, right? You don't need to measure the individual gamma rays. You don't even need to know that it was 3 of them. You just need to know that this was one cascade from the entry state to the ground state. So that was one reaction happening. So when you do that, then the signal looks very simple like this. It's just one peak in your detector that corresponds to the entry state of this, from this level scheme, from this reaction. So this is actually my expertise is in this technique. I've done the summing technique now for 15 years or so. Have applied it both for reactions and for beta decay measurements. And so I'm happy to talk about it later. These are some examples of detectors that use this technique. So they're still pretty compact. So just to get a size, this detector here, SUN, is 16 inches in diameter and 16 inches in length. So it's not a very large detector, but it weighs 750 pounds. So it's a very compact, very dense detector. So it's appropriate for measuring gamma rays with a high efficiency. Oh, yes, there's more questions, please.
Sorry for keep interrupting. On the previous slide, the decay chain shown there, the series of gamma rays, are those in quick succession, or do you need to do something to, if you have a continuous beam, do you have to do something that identifies sort of latent gamma rays from a longer decay chain?
Yeah, no, these gamma rays, So a nucleus, if you produce a nucleus here, they all go with probabilities, right? So there's some probability that will do this one. So one of the nuclei will do this one, another nucleus will do this one. And unless your beam intensity or your reaction yield or the signal in your detector is so high that the detector is overwhelmed, typically, one event will have, let's say, these 3 gamma rays going in different directions, and you measure all 3 and you sum them up. So it would be, each individual event would correspond to a different path of all these available paths.
And sorry, one quick follow-up then. So then you're not necessarily looking to correlate, for instance, the green gamma 2 with the magenta gamma 1, 0.
Yeah, those would never be correlated. Those would never be in coincidence. The only thing that would be in coincidence is the ones that are coming sequentially. So gamma 2 could be in coincidence with gamma 2, 0, because the nucleus could decay like this and then de-excite like this, or gamma 2 could be in coincidence with gamma 2, 1 and 1, 0. But they both start from the same state, so they would never come out in coincidence. 2 different nuclei that would follow these 2 paths.
Yeah, sorry, I meant the magenta 1, 0.
Oh, sorry, 1, 0. Yes, those 2 are in coincidence. And so you would sum them up. So you are looking, in this kind of detectors, you're not necessarily looking for the full energy of this gamma 1, 0, and the gamma 2. And say, okay, oh, there's a peak at gamma 1, 0, there's another peak at gamma 2, sum them up. Because it could be that, let's say if I'm in this detector, it could be that gamma 1 hits here, Compton scatters, so it doesn't get fully absorbed, and then goes over here, and that's where it deposits its energy. But the detector is large enough that it's independent of how many gamma rays it has and how many times those gamma rays scatter around, it will collect all of the energy, and that's what you're looking for.
Thank you.
Yeah. So yeah, these are kind of 3 generations of this kind of summing detectors. This is the one that is at the University of Bochum in Germany. This is the one I did my PhD with, and it's a single crystal. With advantages and disadvantages. You cannot tell how many gamma rays are out there. There were various issues with that. So the next generation that I designed when I joined MSU is segmented it to 8 pieces, 4 at the top, 4 at the bottom. And so then we can tell a lot about those individual gamma rays. And that helps us identify better what's going on and identify backgrounds and stuff like that. And then one of my postdocs who worked with Sun early on, she's now at the University of Notre Dame, and she developed her own version of the detector. And this is the one of the detectors that went into the underground lab that I showed earlier, Caspar. So this detector went there. So yeah, you can see kind of multiple generations. I think I'll move forward from this and switch to inverse kinematics. So in inverse kinematics, I mentioned already that together with the gamma rays that are coming out, you also have a heavy recoil that's coming out, which is advantageous. You can measure that, and you can increase your sensitivity. And this is very, very important because unlike the stable beams where you have a high beam intensity, you still have to worry about backgrounds and yield of the reaction. It's definitely probably 1,000 times worse when you go to radioactive beams. So we need to have the highest sensitivity we can. So I showed already the separator, and I think I'll come back to it. Yeah. So the separator, this is Dragon. There's one that was developed at the University of Notre Dame a few years ago. It's called St. George, that killed the dragon. You didn't get the reference. That's why they called it, I think, St. George. And then at MSU, we just developed a new separator, SECAR. It's the same team that developed both of these detectors. So the idea is that you have the reaction happen at some location. You still have gamma rays around to detect the gamma rays. And then you have this whole thing to reject the unreacted beam and identify the recoils that you're interested in. So you have the analysis in the end is a lot more simple than a lot of the other things we do because the separator does it for you. And you have a detector here in the end, which If your separator worked well, you might end up with a very clean, particle identification, and you do your measurement and of course, life is always harder, more complicated than that. We also have some leaky beam go through and stuff like that, but this is a very powerful technique. A pretty cool idea that I like a lot, I've never worked with this, but I like it a lot, is to get the beam into a storage ring. And you have a very nice thin target. Here's let's say a hydrogen target. So in this experiment, this is a GSI in Germany. So in this experiment, they injected ruthenium-96 beam. And in a typical experiment, when your ruthenium-96 goes through and interacts with the target, it tries once. And if it missed and there was no reaction happen, then that's it. You missed your chance, the beam goes away, it's thrown away, and you have nothing else to do with that beam. But with a storage ring, that ruthenium-96 will go around the ring 1,000,000 times every second, which means that it will go through the target. If it missed, it will try again, and it will try again, and it tries for 1,000,000 times every second. So then it results in something like 1,000,000 times more beam intensity that you would normally have with a regular experiment. It's not as, black and white. There are still losses. It's hard to do and so on, but you do get an improvement compared to other setups. We also applied the summing technique that I mentioned before in inverse kinematics. There's no reason not to. So we're not measuring the heavy recoil. We just still only measured the gamma rays. And this is when I mentioned earlier, the cosmic rays, this is where we had to worry about cosmic rays, and we figured out techniques to reject those cosmic rays and so on. Okay, it looks like it went much faster than I thought, but it's not a bad thing. So let me think. How about I also mentioned a little bit about the reactions with indirect techniques and then stop. Instead of stopping early today, then we might end early tomorrow. So I'll continue for another 10 minutes and then we'll stop. Okay, so indirect measurements. So the same reactions that I just mentioned, ideally you want to measure them in a direct way, but there's a lot of them that you just cannot measure directly. So I have here, my first example is aluminum-26. I showed this picture before with aluminum-26. It's produced in a couple different ways. It could be coming from supernova, and it could also coming from nova explosions. And we can see a clear signal from it coming from the galactic plane. So it's cool to do comparisons with gamma ray observatories and so on. But in order to understand where all of this is created and learn something about this nucleosynthesis in the galaxy, you need to have your nuclear physics well constrained, like everything. And so the reaction with the highest uncertainty right now is this reaction here, aluminum-25 P gamma. And it turns out that this is a very hard reaction to measure. It's just the aluminum-25 beam intensity is not high enough to do this measurement in a direct way. At the energies that are relevant for nova and supernova nucleosynthesis. So instead of measuring this reaction directly, this is an example where here, it's one of my colleagues at MSU. Oh, this got messed up. But it's one of my colleagues at MSU. This was an MSU graduate student, Michael Bennett. And instead of doing the aluminum-25 P gamma reaction, they kind of went in reverse, and they started with the phosphor-26 beam, and they looked for the beta decay into the main level that they were expecting to populate in the P gamma reaction. So it's a complete reverse of the P gamma reaction. But still, they're populating the same level that they would populate in the other way. They can study now its properties. They can see how it de-excites. Does it emit a gamma ray or does it emit a proton? What is the spin and parity and so on? So this is what we mean by indirect ways. You don't measure the reaction directly, but you measure other things around the reaction so you can provide a strong constraint on what that reaction should be. So I won't go into they had a nice gamma ray spectrum, coincidences, backgrounds and whatnot. But the bottom line is that they did measure and study this de-excitation, this gamma ray, and how it competes with the proton emission. And from this, they could get a very strong constraint on this reaction. And they came to a conclusion that about 30% of the galactic aluminum-26 is actually produced in novae, which is a very strong observable or information for us, because what we see in the what we see in the galactic plane, you don't know exactly where it's coming from. Some is coming from novae, some is coming from supernovae, but then we have other observables like iron 60 is another observable that should only be coming from supernovae. So then you can start to have this kind of comparisons and try to isolate which events are corresponding to what kind of event. So this is a cool thing to do. Okay, and then there was one question earlier about neutron captures. So I'll finish here with the neutron captures, which are, it's actually my topic of research lately has been on neutron captures. And remember we talked about regular kinematics and inverse kinematics, but in both cases, if I want to measure a neutron capture on a very short-lived nucleus, it doesn't work. So either you have a neutron beam hitting a short-lived target, but you cannot make a target that lives for 2 seconds. So this is impossible. And then in the flipped, I can make it a beam of a nucleus that lives for 2 seconds, but I cannot make a neutron target either, at least not in any way that it would be enough yield to do these measurements. So because we're stuck with this kind of issue, it's a pure experimental issue, but it's an issue and we cannot do these measurements right now, then we have to come up with indirect techniques. I mentioned there's some cool ideas for how to do this in the future. One idea is to do 2 beams hitting each other, but again, the yield is not high enough. There's an idea to get the heavy beam in a storage ring, so we amplify its intensity. That would also be cool. So there's a lot of ideas, but nothing set in stone yet. So we need to wait another decade or so before we can get anything reasonable out of this. So we're stuck with these indirect techniques. So let me tell you how those indirect techniques work. So it's a similar story as with the aluminum-26 example. You want to measure this neutron capture on some nucleus. And so it's a neutron capture populating this, we call it the compound nucleus, which de-excites by emitting gamma rays. So the idea is, what if I populate this nucleus in a different way? Maybe something that mimics the N gamma reaction. And then again, I can learn enough about the reaction products that I can constrain my neutron capture. So one technique is called the surrogate technique, where they use different reactions, but the most obvious is a DP reaction. So instead of just a pure neutron, you add a proton to it and you have a deuterium, and then you have the proton is coming out afterwards. So it's still an N gamma kind of reaction. And when they do that, they measure all the gamma rays that are coming out, and from these gamma rays, they can kind of constrain the reaction that's taking place. Another technique that my group is using is called the Oslo method. Again, I'm not going to go into a lot of detail, but it's based on the fact that out of these nucleus, the main ingredients that we need to calculate these neutron captures are the characteristics of the nucleus itself, and they're the statistical properties of the nucleus that I mentioned before. So I mentioned the nuclear level density. This is an important quantity. The gamma ray strength function is the probability to emit all of these gamma rays. So that's also a very useful quantity. The optical potential, it doesn't matter very much, so we don't deal with it, at least for now. But you see the impact of all of these quantities here. So this is cross-section as a function of energy. And if I vary the nuclear level density using just different models, I get a factor, it's almost a factor of 10 uncertainty in the predictions of these models. And the same is true for the gamma ray strength function. So if I can go experimentally and constrain this gamma ray strength and this level density, then we can get a cross-section that is a lot more reliable than if we just rely on theory without any experimental input. So this is kind of the idea behind this. I'm not going to go into a lot of details, but this shows you how we think about things. So again, this is the nucleus. You can come to it from this side through some kind of a reaction. We do it through beta decay, because the advantage of beta decay, it's actually for anyone who is doing reactions. Beta decay is something very exotic, because if you're doing reactions, you have a certain amount of beam particles. You can have 1 million beam particles coming down the pipe, but not all of them will interact. Maybe one will interact every second. So you have very few reaction products to measure in the end. But if you're doing beta decay, if you have just one particle every second going into your detector, then you will have one particle every second decaying. They will all decay. So all of a sudden, you can do experiments with beam intensities that you didn't even dream of having before, with one particle per second, and you still have enough statistics, enough yield to do all of this. That's why we switched to beta decays to do these kind of indirect techniques. So again, what we're trying to do is learn enough about the nucleus to constrain the neutron capture cross-section. I'll just show you an example here. This is for one of the R process, the lighter mass R process nuclei. We focused on this region to start with. This is the reaction that we were trying to do, 69 nickel and gamma. Then the half-life of 69 nickel is 11 seconds, so you couldn't even dream of making a target out of this. And what we do is populate that same final nucleus through the decay of cobalt-70, the beta decay, and again, learn enough about nickel-70 to do a constraint. So this is the kind of constraint we're providing. This is, instead of a cross-section, I have here the reaction rate. We saw this before. This is the uncertainty. The light color is the uncertainty coming out of the theoretical predictions. It's a pretty big uncertainty. And the blue band is what we get through this indirect technique. So it's not the same as measuring a reaction directly, but we are providing a strong enough constraint to have an impact on astrophysics. Okay, and now I will stop here with my neutron capture reactions, and we'll talk about nuclear structure tomorrow. So let's take a 10-minute again, go into breakout rooms, have you guys should come up with questions, and we come back at 11:10 to answer those questions. So everyone's back. I'll start by answering Alex's question that he put in the chat earlier that I didn't get a chance to answer. So the question was, do you lose any kind of resolution when switching to beta decay due to the large kinematic range of the products? The answer is that you don't really lose in resolution, because even though, let me see, do I have, yeah, even though, let's say when you have a beta decay feeding a level over here, that beta particle could have any kind of energy from 0 basically to the full available energy, and we don't know that. This is not how we measure the excitation energy of the final nucleus we populate. The way we measure that excitation energy is again from all the gamma rays that are coming down. That's why you need, remember I mentioned before in the reactions section that we use this large summing detector. You use that kind of detector here as well. And then you get your excitation energy from the gamma rays. So then it doesn't really matter what the beta energy is and the fact that there's a huge range. The beta for us is just a trigger. We don't really use its energy for anything else. Okay. Breakout room, let's start in reverse. Breakout room 5.
Hi, so a question about the summing detector technique again, actually. I didn't quite get the experimental technique for how that works. So was it like these different detector at different angles and the different angles measure different gamma coming out of the target? Is that how that works?
So again, if I come here, at the center of the detector, I don't know if I have a better picture. I'm sure I have it, but just not on this presentation. So all of these gamma rays are emitted at the target location. So that's at the center of your detector. And now imagine, let's say in a perfect world, you cover 4 pi of the solid angle around your target with your detector. So then each of these 3 gamma rays could be going in a completely independent direction. There is some angular distribution, but even that doesn't matter because you're collecting all of the energy. And so let's say if all of your gamma rays just do photoelectric effect and get fully absorbed on the first hit, then you would have 3 hits in your detector, 1 hit that has all of the energy from gamma 2, 1 from the gamma 2.1, and 1 from the gamma 1.0. You measure those 3 hits, those 3 energies, and you sum them up, and you get 1 count at this location right here. Does this make sense so far?
Yes.
Okay. So now things are, of course, more complicated in the real world. So each of these gamma rays could also not get absorbed at the first hit, but it could scatter off and go and interact again. Again, if you have a large enough detector, even this doesn't matter because after the scattering, you will still get absorbed at the next step. So again, you collect all of the energy. But you have to have a large enough detector to do this. If you start to have smaller detectors, or your detector has holes, or it has, dead material in between and so on, then you start to lose all of that. So instead of having just an ideal peak like this, you would still have a peak ideally, but you kind of have a tail that goes all the way to low energies because of all the losses. But even in that case, it's not the end of the world because you can calibrate your detector and say, okay, if I have gamma rays coming from this excitation energy and it's 3 gamma rays, then this is the efficiency of my detector to get a count in the sun peak versus have a tail that disappears. So if you calibrate your detector enough, again, you can get the cross section. Our goal here is to know how many of these final nuclei did I make. And in the previous case, you would measure individual gamma rays. And in this case, you measure the full energy. But again, each count in your peak would correspond to 1 nucleus that was created. Does this help?
Yes, thank you.
Okay. Group 4.
I had a question. So I know you kind of already stated why, but I was wondering if you could go more in depth as to why beta decay is like the superior decay to use here.
Yeah, I wouldn't say it's superior. Beta decay has different problems and so on. The biggest advantage is that with beta decay, every single particle of your beam that you implant at the center of your detector will decay. So you can go a lot more exotic in terms of the isotopes that you can reach. So I can do experiments with beta decay down to about 1 particle per second. And that brings me a lot further away from the stable isotopes into the R process region, for example, definitely into the I process region. But if you want to do a reaction to do the same thing, then because not every particle that hits your target will do a reaction, it's actually far from that. It's a very, very small fraction of the particles that hit your target that will actually react with your target and give you a reaction product to measure. So you need beam intensity. If you do a reaction, you need beam intensities 10 to the 4, 10 to the 5 particles per second at least. That's 5 orders of magnitude. So the main advantage and why we switched to beta decay is because you can apply these techniques a lot further away from the stable isotopes into more exotic and closer to our process nuclei. Make sense?
Yes, that does. Thank you.
Okay. Group 3.
Yes. Hello.
Hi.
Okay, I have another question about neutron, and more specifically neutron target. Why we can use something like helium-4 or deuterium as a target, and why it doesn't work?
You can, but it's still not a free neutron to do a capture. So
Yeah.
you get more into, oops, something like this. So what is called the surrogate method. So instead of doing n neutron plus the, this is in my way. Yeah, so instead of doing the neutron plus your target, you could do like a deuterium plus your target, and then the proton is coming out. So again, the neutron is the one that got transferred into the target. So it's a pretend neutron capture, but it's not 100% neutron capture. The angular momentum considerations are different. The excitation energy that you populate is a little different. The reaction mechanism is different. So all of that come into this surrogate method to, in the end, extract the neutron capture from a DP reaction, for example. So it's similar, it's just still not the same. That's why it's still considered an indirect technique.
Okay.
Okay, let me see. There's a follow-up. Okay. That's oh, normally we said one question per group, but since I got distracted here and reading it, typically from the spectral lines do not correspond to this kind of gamma ray decays or reactions or whatever. The spectral lines are just if there is an element, a particular element in the stellar environment, it's more of atomic lines, let's say, than nuclear lines. The only case where we do see the real gamma rays is in like in the aluminum-26 example that I gave here. All of these gamma rays, all of this signal is actual gamma rays, and this is a peak of actual gamma rays from the decay of aluminum-26. It gives you a peak at the 1800 something, and so then you can measure, you do measure the real gamma rays, but in every other case, it's just what is there in the environment. The gamma rays that are produced from this kind of reactions, they go all over the place in the star. They get absorbed by the star. They get re-emitted. Their signature does not survive to make it to us. Okay, group, I lost track. Group 2.
Okay, so you talked about how you have heavy projectiles and light projectiles, right? Mm-hmm. So now, like one possible reason, what I understood was maybe if heavy projectiles, if they decay really fast, so you accelerating them would mean that because of time dilation, their decay takes a longer time. So then you can use it as a beam. But what other reason would you have for using heavy projectiles?
It's not the time dilation or anything. It's just a production mechanism. So then we go back to what we had. We'll get there. I think I went too far. Here. So this part, to create the first fast beam in a fragmentation facility, it can take however long, it doesn't matter. You put a stable isotope in your ion source, it gets ionized, and then it gets accelerated through the accelerator. But this is still all stable. But from this moment when your fast beam hits the target, this is where those radioactive isotopes are produced. And then from this moment that they're produced until they make it into your experimental setup, it's a few tens or hundreds of nanoseconds. So anything that lives for longer than a few nanoseconds will be delivered to your experimental setup and you can study it. So this is the main reason why we can do these experiments with things that typically beta decay can go up to a few milliseconds, doesn't really go less than that. So any nucleus that would beta decay with a half-life of a few milliseconds, we can definitely produce and study and get it into our experimental setup and study. Yeah, that's why you switch to your kinematics, you switch the other way. Make sense?
So now, I mean, there's always the option that, let's say, these projectiles decay before reaching the detector. You can always study the decay channels, right?
If they decay before making it into your detector, then you cannot, well, I guess if the decay product is also coming down the pipe, then you could detect the decay product. But as I said, there's very, very few. Okay, we talked on the first day about neutron decay. The neutron decay could happen, and it happens much faster. It would happen right at the target location, for example. And then the thing that would get propagated through could be the daughter, the final product of that neutron decay. But anything else typically will live longer than that. Like, as I said, beta decays a few milliseconds, that's plenty of time. There's some isomeric states that are of the order of nanoseconds. So in that case, maybe, you know, some of it decays in flight, but the majority, the vast majority will make it to your experiment. Group one.
Hi. So we were wondering if you could tell us a little bit more about the methods for calibration. I think you mentioned on slide 114 or something about these different kinds of detectors. So what I'm used to in my research is having a Monte Carlo generator pass through a simulated version of the detector to calculate efficiencies. Do you do that, or do you do actually some kind of like experimental calibration, or a mix of both?
It's a combination of the two. So for us, we use typically radioactive sources that will produce known gamma rays. And then we use those to, at least for the energy calibration, then we use those. But those have a limited energy range. So maybe we have 5 different gamma rays to do our calibration. But then anything in between, we can validate our GN4 simulation with the known sources. And then anything in between is basically coming from the simulation. And similar for the efficiency of the detector. So we need sources that are very well calibrated, you know, the activity, you know, when they were produced, then you need to know the distance from your detector and so on, and you get an efficiency. And again, you will get 2-3 efficiency data points, and everything else is done through a simulation once you validate it.
Okay, thank you.
Oh yeah, we went through all the groups. If anyone has any question, open to all groups.
Yeah, I have another question.
Sure.
Again on neutrino. Can we use something like helium-6? I think you speak about that in the first lecture, that helium-6 is not helium. Lithium-6 is an atom with an halo of neutrino. I think.
Lithium-11 has a halo.
Oh, okay.
Again, in principle, you can do this and then transfer. So this category of reactions are called transfer reactions. So somehow you have a nucleus, you use a nucleus where the last neutron is loosely bound. And when it interacts with your target, then the neutron gets transferred into the nucleus and the rest flies off, and you can measure what flies off. So lithium has been used. It would be, yeah, I have to think now. Lithium-6, I think, is a good one. Beryllium-9 is a good one because everything is paired except then the last neutron. So there are reactions like this, but then you go into heavier nuclei and the cross-section, because of the Coulomb barrier and whatnot, gets smaller and smaller. That's why, and also it's a more complex target. So that's why the deuteron is the best choice, because just one proton, one neutron, we kind of know the interaction between them. And then the reaction part that you're trying to isolate your neutron out of your target is just simpler. But yeah, all of these techniques have been used to some extent. Other questions?
On reference to your readout electronics, what's usually the rate at which the readout electronics interact, like in terms of kilohertz, for example?
Yeah, that varies a lot depending on the experiment. With our experiment, we try to keep it less than maybe 20 kilohertz. We try not to go too much higher than that, because the sodium iodide and the silicons are not the fastest detectors, and you don't want to have pileup and so on. So we check that up to 20K is still okay to use, and we can reject pileup or not have too much. We haven't done it more than that. Some of our beta decay experiments, we actually try to stay less than just 100 particles per second in total. And so that is not a very high rate. And that's so we can identify when each ion got implanted and when the beta decay happened following that implantation. So then you need a low rate to be able to identify this kind of correlation. There are other experiments that try to go to much higher rates, but for our experiments, we typically don't.
So I guess if nobody else wants to ask a question, I'll just keep asking questions that I had from the previous time. So it seems that we have a couple of labs that are involved in this type of research. And I wonder, what's the type of collaborations that you guys might have with perhaps some other universities? Like, I know, for example, the Florida State University has a partnership with the University of Florida, and they kind of like share the resources, but I don't know if that's the case with Michigan State or some other lab. So
yeah, so Michigan State, the facility is a user facility like JLab, for example. So anyone can submit a proposal, and if it gets accepted, they can come and run their experiment there. That's so in a sense, that is sharing of resources within the community. It's a DOE supported lab, so anyone can come and run their experiment. Otherwise, it's collaborations, kind of individual PI collaborations. I have a colleague, for example, who works very closely with someone at Mississippi State, and they have students and postdocs stationed at MSU because that's where they will run their experiments, so they want to learn. So we have frequently students or postdocs who will come for maybe a few weeks or months before their experiment to set up their experiment and run it, and then they return to their home institution. I run a lot of experiments, not just at EFRI, but also at Argonne National Lab. So my group goes back and forth. It's a 3-hour drive for us, so it's not that hard to do, but still we'll go back and forth. I work a lot with the University of Oslo, for example, in Norway, because of the technique that they develop, and then we upgraded and so on. So they've spent months at MSU for research and collaboration. So I would say it's this kind of collaborations.
Thank you.
Anything else?
Okay, I don't see any other question. So I would thank Artemis in a virtual way. I can clap for you. So, okay, I did it for you. And so thank you, Artemis. I think we can reconvene at 1:30. And if there are other questions to Artemis today, just put on Slack, and she will probably answer if she has time today. And we are kind of thinking of having kind of a recap session after the lectures today, but just stay tuned on Slack to know what is going on, because we are still reorganizing everything for this week.